Welcome back to chemistry, and with this presentation I'm going to be talking about a few different things. And so one of the things I want to do is compare the difference between nuclear reactions and chemical reactions. And so nuclear reactions are covered in section 20.1 in your book. Another thing I want to talk to you about is ions, which is in section 2.4 of your book. And then the last thing I want to go over for this presentation is the difference between molecular and empirical formulas, which is covered in section 3.1 of your book. Okay, chemical versus nuclear reactions. So what you need to understand is most of what we're going to be talking about in this chemistry class is chemical reactions. And so one thing to keep in mind when we're dealing with chemical reactions is that when you see elements binding together to form compounds, for example, you should know that the nuclei of those elements are really not changing during a chemical reaction. So if you have a chemical reaction and you're dealing with two elements A and B, and let's say those two elements have a certain number of protons and a certain number of neutrons, and they combine to form the compound AB, in the compound AB, those protons and neutrons will be the same number as the elements that combine to form that compound. So in chemical reactions, there's really no change in the dispositions of the protons and the neutrons in the elements. However, what does change in chemical reactions is where the electrons go. So in a lot of chemical reactions, which you'll learn about in the next chapter, a lot of times, although the atoms are combining and the nuclei are not changing, electrons will be leaving one atom and going to another. Other chemical reactions are different. You have one atom sharing its electrons with the other and vice versa. And so we'll talk more about that later. So here's an example of a typical chemical reaction. So this is an unbalanced equation for the formation of rust. So we see one element there, which is iron. And so we see it combining with another element, oxygen, in the air. And in the presence of water, which acts as a catalyst, we have iron combining with oxygen to form the compound iron oxide. This is a chemical reaction. And the reason why it's a chemical reaction is because you can look at this equation and you can sort of see that the elements are not changing their identity as you go through the reaction. On top of that, the elements are basically not changing their identity, but their atomic numbers and mass numbers of the nuclei of these elements is not changing. So for example, with the iron we started out with, it is iron, so you can look up its atomic number, which is 26. In this example, it has an extra 30 neutrons, so the mass number is 56. And so when that iron combines with oxygen, what you can see is that the atomic number and the mass number of the iron is still the same. That did not change. Same thing with the oxygen. Oxygen has an atomic number of 8. It also has 8 neutrons in this example, so it has a mass number of 16. And what you can see is those numbers, the atomic number and the mass number of the oxygen, did not change in that reaction. So this is not a nuclear reaction. This would be a chemical reaction. Again, all that is changing is how the electrons are being shared between iron and oxygen. Okay, so I just got through describing an example of a chemical reaction. So now what I want to do is give you an example of a nuclear reaction. So what I want to do now is take the iron atoms that we had before. And so the iron atoms, all iron atoms have 26 protons, and so they have an atomic number of 26. Now, the particular iron atoms we were looking at also have 30 neutrons, and so the mass number should be 56. Now, let's say we took these iron atoms and we took them to a nuclear reactor. And at that reactor, that's a great source of high energy, high speed neutrons. And what we can do is we can expose these iron atoms to neutrons. And for each iron atom, it will react with 4 neutrons. And let's think about what is going on in this reaction. The neutrons, the 4 of them, are passing basically through the electron cloud of the atoms, and then they're sticking into the nucleus. So the iron atoms did have 30 neutrons. Now they have 34 neutrons, and they become this. So they become iron, but because it has 26 protons, it's still iron, right? But now each iron atom has 4 additional neutrons. So now we're up to 34 neutrons, and so its mass number is 60. So one of the things you can see here that has happened in this reaction is that we have changed the kinds of particles that are in the nucleus when we've gone from reactants to products. So as a reactant, the iron atom had 26 protons and 30 neutrons, but as a product, it has 26 protons but 34 neutrons. And so for this reason, because the number of neutrons is changing, this is considered to be a nuclear reaction. So here's a sort of another way of representing this formula that you might see in a textbook. A lot of times we write out symbols and we include the mass numbers without including the atomic numbers. And so what we have here is just basically the same thing up there, but we're not indicating what the atomic number is. And so I guess the point I want you to sort of know is if you have evidence that the nucleus in an atom is changing for some reason or another, maybe it's picking up extra protons or extra neutrons, or both protons and neutrons at the same time, or maybe it's losing protons and neutrons as you go from reactants to products, that would be an example of a nuclear reaction. So in summary, if for some reason you see that when you go from reactants to products that the nucleus is changing in its particles that it has, then this is a nuclear reaction. So I want to talk about some particles that leave nuclei during nuclear reactions, and this becomes important when writing out equations for nuclear reactions, and so I'm going to write this on the computer screen. So these particles are part of the forms of radioactivity that I introduced to you a couple of presentations ago. So one of the particles is called an alpha particle. So I'm going to write alpha here, and its symbol is the Greek letter alpha like this. So I'm going to write alpha like this. That is one symbol. Now you might remember from the last presentation what the alpha particle or alpha bit of radiation is. What it is basically a helium nuclei. So it's going to have 2 protons and 2 neutrons, but no electrons. So the way we can sort of designate that is that if it has 2 protons, it's going to have atomic number of 2. If it has 2 neutrons, it's going to have a mass number of 4. So this is a nice way of representing that. Or a lot of times you'll just see it as an alpha, but you should know that refers to a helium nucleus. Another way you can refer to this is because it is a helium nucleus, you can write the symbol for helium and an atomic number of 2 and a mass number of 4. So A is the mass number. So the alpha radiation will have a mass number of 4. Z is the atomic number, so the Z number is 2. Now, you have to remember that this is a helium nucleus. Normally, helium has 2 electrons, except in this case. If it's just a helium nucleus, there are no electrons there. So it's going to be deficient in 2 electrons. And so basically, it's got 2 protons, which each have 2 positive charges, which is not balanced by 2 electron negative charges. So this will have a 2 positive charge. And again, in terms of identity, this is just a helium nucleus. So the next kind of particle I want to talk about is something called the beta particle or beta radiation. So that's the Greek letter for beta. I'll write B-E-T-A. And so you could write a beta symbol like this. Now let me talk about what it is and talk about how you get it before I give you the additional information, which is a little bit unexpected. So what the beta particle is, it's an electron. And so it's going to be negatively charged, so I'll put a negative charge there because it's an electron. But here's the thing. With beta radiation, when an atom is emitting it, it's not taking one of its electrons in its electron shells and shooting it out. Something different is going on. What's going on is in the nucleus, you have a neutron converting into 2 particles. One is a proton and one is an electron. And that electron is spat out of the nucleus. And that electron that's spat out is the beta radiation. So let me show you how that works, because it's, again, it's a little bit unusual. So imagine some kind of nucleus. So there's a lot of protons, a lot of neutrons. So I'm drawing P's for protons, N's for neutrons. So just a lot of protons, a lot of neutrons. I'm not even counting them. So this is, again, the nucleus of an atom. Now, what can happen every once in a while within the nucleus of an atom? The neutron will spontaneously transmute. It will convert to two different particles. The neutron will stop being a neutron and become two different particles. One of the particles is a proton. I'm going to remind you that that proton has a positive charge. The other particle that is created at the same time, and it must be created at the same time as the proton, is an electron, which has a negative charge. Now, you might wonder, why did this happen? Why is the neutron creating these two oppositely charged particles? And the reason is the neutron has no charge, right? And so to have charge balance in this nuclear reaction, if you create a proton which is positively charged, you must create a particle which is negatively charged. So that would be the electron there. So that is something to keep in mind, which is very important with the beta particle. Again, it's an electron. It does not come from the electron shells. It actually comes originally from a neutron that broke up into a proton and an electron. Okay, so with that information, we can carry on. So what are the symbols for the beta radiation? So one is beta. You can also write in beta minus. Now, another way to write this, which is kind of strange, is you can sort of associate, if you will, a mass number and a atomic number with this beta particle. So the mass number, we can think of it as 0. The atomic number for this particle is not what you would expect. So what is going to happen is that when this electron is spat out, you're basically taking a neutron and turning it into a proton. And so you can think of this as having a -1 atomic number. That seems a little strange, but this will become clearer later when we do problems. So the mass number is 0. The atomic number, Z, is -1. This will become clear again when we're doing a problem. And the charge of the beta particle is negative. It's -1 because it is an electron. Okay, and then the final particle that's created is gamma. So this is actually not a particle. It's really thought of as more as electromagnetic radiation. And so its symbol is gamma. There are really no symbols. Other symbols, maybe you could write gamma. There's no mass to it. It's a massless particle, so it's a 0 for mass number, and it doesn't really have an atomic number there. So these are 0, and there's no charge. And so this is high energy radiation. Okay, so let's move on to some problems that you might face on the test. Okay, so problem number 1, write out a nuclear reaction where uranium-238 releases an alpha particle. So let's kind of walk through that and how you would do that. Okay, so we have uranium-238. Okay, so we're going to give an example here. We're going to write out an equation where the uranium-238 is spitting out an alpha particle. So we have to figure out what the uranium-238 becomes. So before we figure that out, let us write out uranium-238 in symbol notation. We should be able to do that because we know what the element is, and we can look up the atomic number for uranium on the periodic table, and we know what its mass number is. So its symbol notation is U. So the atomic number for uranium, which you can look up in the periodic table, is 92. The mass number is 238. Okay, so the question is this. Uranium by itself, uranium-238 is radioactive. Every once in a while, it will spit out an alpha particle. So we're going to get some kind of element after this nuclear reaction. But one thing we do know is we get an alpha particle that is released. And we do know that the atomic number of the alpha particle, because it's a helium nucleus, is 2, and the mass number of the alpha particle, again, because it's a helium nucleus, is 4. So now, can you figure out what remains when uranium-238 isotope spits out a helium nucleus? You should be able to figure that out. So one thing that is happening is that the uranium-238, it has an atomic number of 92, is losing 2 protons to this alpha particle. So what is left at uranium-92, the 92 protons, is losing 2 of those protons, and so we should have 90 protons left. So that should indicate to you that this is no longer uranium, because it has a different atomic number, then it's going to be a different element. And so you can actually look that up. You'll have a periodic table on the test, and so the atomic number of 90 is associated with the element called thorium. Its symbol is Th. Now, what happens to the mass number of thorium? Or what happens to the mass number of uranium? What is going to be the correct mass number of the product thorium? Well, you can see uranium is spitting out an alpha particle which is taking 2 protons and is taking 2 neutrons with it. So basically we're losing from the 238 a mass number of 4, so it should be a mass number of 234 associated with the thorium. So that is correct. Okay, let's go on to the next one. So now problem 2, let's do that. Write a reaction where uranium-238 releases a beta particle. So what I'm going to do is write out uranium again. Its atomic number is 92, its mass number is 238, but this time it's not releasing an alpha particle, it's releasing a beta particle. So as you might remember, it is a electron, so its mass number is 0 because it has no protons and neutrons. But the way we think about the atomic number for a beta particle is -1. Now, let's think about what happened. So we had uranium with its 92 protons and some number of neutrons. And what happened to release the beta particle is one of these neutrons, it spontaneously converted to form 2 particles. It formed the negative electron, but at the same time, it formed a proton. So what we need to do is we need to account for that in this equation. So the product of this reaction, when you have a uranium nucleus with 92 protons and some number of neutrons, then the neutron loses an electron, then a proton is formed. So if the proton is formed, then uranium should have an atomic number of 93. But here's the problem. It is no longer uranium because it has a new atomic number. So I erased the U there. Instead, if you can look up the atomic number of 93 and see what element it's associated with, the element is neptunium. So we would have to put an NP there for neptunium. So now, does the mass number change? The mass number change for the beta emission? No, it's still at 238. And now another thing you can sort of see is that these numbers on the top of the equation with the mass numbers before and after the nuclear reaction should be equal before the reaction to after the reaction. So we have 238 mass number before the reaction. We have 238 in the neptunium plus 0 in the beta particle for a total 238 after the reaction. How about for the atomic number? We have 92 for uranium before the reaction, and then for neptunium, we have 93 minus 1, which should be 92, so that adds up. So this should be correct. Okay, let's do the final problem. Write a reaction where thorium-234 releases gamma radiation. So this is actually pretty simple. So thorium-234, so thorium is Th, is the symbol. The mass number is 234, so that goes in the upper left. Thorium, you can look up what its atomic number is 90. The good news is if it's releasing gamma radiation, the problem is simple because the gamma radiation does not affect the number of protons or neutrons and electrons in the nucleus. So basically, if you have this thorium atom with this number of protons and neutrons, then you're going to have the same thing after it releases the gamma radiation. So for problem 3, this should be correct. Okay, so let's move on. Okay, so the next thing I want to do is talk about ions, and so I'm going to sort of fill out some blanks here on the screen. So just to note that atoms that are neutral will have an equivalent number of protons and electrons, but as soon as the atom gains or loses 1 electron or more, it's no longer a neutral atom. It is called an ion. So let's give you an example of elements that have a certain number of protons and electrons to start with, but here what we're doing is adding electrons to them. Let's talk about what's going on here. So in the case you have an atom and it's gaining electrons, it's gaining negative charge, the resulting ions are called anions, A-N-I-O-N-S. So an anion is the case where the atom has more electrons than normal. So here's a good example. The first example is you have fluorine. Fluorine has an atomic number of 9, so it has 9 protons in it, so it should have 9 positive charges. Normally fluorine is neutral, and so it would have 9 electrons, but let's say you were able to add 1 electron to it, then it would have 10 electrons. And so now you have 9 protons, 9 positive charges, and 10 electrons, 10 negative charges. So we have 1 more negative charge than positive charges, and therefore the atom has a net negative charge. And so the way we indicate that is here with this symbol here, we have F minus. So that indicates that the fluorine atom has a net 1 negative charge and therefore is an anion. Another example, we have phosphorus. Normally it has 15 protons, which has 15 positive charges, and it would also normally have 15 electrons and 15 negative charges. Let's say we were able to give it 3 additional electrons. Then we bump up the electron count for this phosphorus atom from 15 negative electrons to 18 negative electrons, which is too many electrons compared to 15 protons. And so there are 3 extra electrons. So to indicate that this new atom of phosphorus has 3 extra electrons, we write this symbol here, a P with a 3 minus. In the case that an atom is losing electrons, then the atoms, after they've lost the electrons, they have a deficiency of electrons. They are called cations. And so here are a couple of examples of that. So we have sodium, for example. Normally it has 11 protons or positive charges, 11 electrons and negative charges. But if it were to lose one of those electrons, we're now down to 10 negative charges, but we still have 11 positive charges. So it's deficient in a negative charge. So the way you can think about it, it has an extra positive charge. So if it has an extra positive charge, the way you symbolize that is with an Na+. Calcium in this example normally has 20 protons and positive charges and 20 electrons and negative charges. If it were to lose 2 electrons, you're now down to 18 electrons. It has a deficiency of 2 electrons, which means it's got 2 extra positive charges. And so it's going to be, the charge of the calcium ion will be Ca2+. Okay, so moving on. Okay, so now let's go ahead and try to fill out this chart. This is another sort of good exercise and something you might see in your test. So given those symbols that include a mass number and a charge for the ion, can you tell me how many protons, neutrons, electrons are in the atom represented by the symbol? So let's do the first one. So with aluminum, you would have a periodic table, and so to figure out the number of protons, the best thing to do is to look up what the atomic number for aluminum is. The atomic number for aluminum is 13, and so it has 13 protons. With neutrons, it's going to, you can figure that out, right? So the mass number is 27. There are 13 protons, and so you can figure out there should be 14 neutrons. Now, how about the electrons? Now, keep in mind that because we have a 3+ charge with that aluminum ion, it is not a neutral atom. Since it is a positive charge, that indicates that it has lost electrons. It has a deficiency of electrons. And so if that is the case, if it was a neutral atom, it would have 13 electrons to match the 13 protons. But again, it has lost 3 electrons. It has a deficiency of electrons, so it only has 10 electrons. Okay, for the next one, selenium. It has a mass number of 80 and a charge of -2. So the atomic number is 34. So can you figure out the neutrons given the mass number? It's going to be 80 minus 34, and so it's going to be, what, 46 neutrons? Okay, now how about the electrons? Again, this is not a neutral atom as indicated by the 2 negative charge, so it has an excess of electrons. So normally in a neutral atom, because it has 34 positive charges, it would have 34 negative charges, but we have an excess of electrons. So there's 2 more than 34, so it should be 36 electrons. Now, the number of protons in neon is the same again as the atomic number, and so I know the atomic number of neon is 10, so remember that one. And so the number of neutrons in neon in this example should be what? It's going to be 12. And then neon, you will note there's no charge symbol there on the upper right. There's no negative symbol, there's no positive symbol. So we should assume the neon atom is neutral charged. If it's neutral charged, it'll have as many electrons as protons, so there should be 10 electrons there. Now copper, the atomic number of copper, the number of protons in it is 29. The number of neutrons will be 63 minus 29. Let's see, what would that be? It'd be 34. Okay, so note that the copper ion there is 1 plus. That means it's missing an electron. So you'll have to associate a positive charge with missing electron from neutral atoms. So neutral, if it was a neutral atom, which it's not, but if it was, it would have 29 electrons, but it's missing 1. So we should have 28 electrons here. Okay, moving on. Okay, types of chemical formulas. And so there are 4 pictures of chemical formulas there. And so one is where you have elemental symbols kind of stuck to one another. And so that example there is of a molecule where you have 4 hydrogen atoms bound to a carbon. This molecule is called methane. And so there, when you see CH4, that is a molecular formula. The molecular formula tells you with subscripts, the small number on the right there, on the bottom is a subscript. It tells you with subscript how many atoms you have for each element. So here is the molecular formula for methane, which is CH4. Again, we have 4 hydrogen atoms with the carbon. With B, we have a structural formula. That just shows you with lines how the carbons and the hydrogens are connected by bonds. Then we have a ball and stick model, which is sort of a nice picture, a 3-dimensional structure that shows you again how the hydrogens are attached to carbons. But in fact, the molecule does not really look like that. And if you had a super powerful microscope, you would not see bonds like that. Instead, it would look more like the space-filling model, where you have sort of hydrogen spheres that are smaller than the carbon sphere, kind of stuck to it. So that is a space-filling model. So those are several models there. So now what I'm going to do is talk to you about the difference between molecular and empirical formulas. So I think the best way to describe that is through several examples. And so we have a structural model of a molecule called butene. And so you can count the carbons in that model, and what you'll see is that there are 4 carbon atoms. And if you count the hydrogens carefully, the top carbons have 3 hydrogens attached. So the top part of the molecule has 6 hydrogens, and then there's 2 on the bottom, so there are 8 hydrogens. And so the molecular formula reflects the actual numbers that are there in the structure. So the molecular formula should be C4H8. Now, what the empirical formula is the molecular formula where those subscripts are reduced to the smallest whole numbers possible. So if you look at 4 and 8, it looks like they can be divided evenly by 4. 4 goes in the 4 1 time, 4 goes in the 8 2 times. And so the empirical formula is just CH2. Let me give you another example. Here we have some models of another molecule. The molecule is called benzene, and if you look carefully at those structures, you will see that there are 6 carbon atoms and 6 hydrogen atoms. And so if that is the case, the molecular formula again indicates the total number of atoms for each element in that structure. So it should be C6H6. Now, what is the empirical formula? Can you take C6H6 and reduce it to a simpler whole number ratio? Is there a number that goes in evenly into 6? And the answer is yes. 6 evenly goes into 6 one time. So the empirical formula is just reducing the 6's as far as you can go. They can be divided out by 6, and then you're left with 1. So the empirical formula is just CH. Okay, so the final thing I want to go over, for these molecules, I want to indicate a molecular formula. and an empirical formula. Okay, so the molecular formula for butyric acid, all you have to do is count up the atoms. So it looks like we have 4 carbon atoms, and it looks like we have 1, 2, 3, 4, 5, 6, 7, 8 hydrogen atoms, and we also have 2 oxygen atoms. Now the question is, can we reduce the molecular formula further into simpler whole number ratios? And the answer is yes. And so we can get an empirical formula that is different from the molecular formula. So it looks like we can divide all those subscripts evenly by 2. So the empirical formula should be C2H4O. Okay, let's look at glycine. It looks like we have 2 carbons. We have 1, 2, 3, 4, 5 hydrogens. We have 2 oxygens, and we have a nitrogen. So that is the molecular formula because that is the actual count of the atoms for each of the elements. Now, can we divide those subscripts such that we can get a formula with lower whole numbers? And I cannot think of some number we can divide 2, 5, 2, and 1 into evenly. So we cannot really reduce that formula into a smaller whole number ratio. So the empirical formula in this case is exactly the same as the molecular formula. So the empirical formula for glycine is the same as the molecular formula, is C2H5O2N. Now how about adenine? So how many carbons do we have? We have 1, 2, 3, 4, 5. 5 carbons. It looks like we have 5 hydrogens, and it looks like we also have 5 nitrogens. And so that is the molecular formula again, because we're actually individually counting atoms in that formula for each element. So what is the empirical formula? Is there a number that will go into evenly to all those 5s? And the answer is yes. That number would be 5, right? It would go into evenly 5 one time. So the empirical formula is just CHN. Thank you for listening. We'll see you next time.